than the calculator. We're even seeing disruption in the 21st century Kanban. Here's a Kanban example of Amazon Prime where you can order things like putting out a Kanban card and getting it delivered by Amazon. The Amazon effect is disrupting brick and mortar and shopping for many individuals. We even have disruption in data. Historically, because we did not have technology, we did things by sampling. I took a whole semester of sampling class in graduate school. Now with technology and the ability to look at data warehouses, databases, data lakes that all people are talking about, if you have any of those available, you have then significant amounts of data that you can analyze without having to do sampling. You can draw inferences on larger sets of data and see more things that are going on. So now let's look at the voice of the customer and look at the disruption that can be used to get better information from our customers, because we want to find current trending, if we're working on new products or markets, and if we're creating new products or services. Let's compare surveys to social media. Traditionally, surveys ran through this process. We had to choose the type of survey, get the questions put together, what's the sampling frame going to be. We implement it, follow through to maximize our response rates, analyze it, and write a report. Significant amount of time spent, and we didn't know that from the time that we chose the type of a survey in bullet 1 until we wrote the report, how much time had elapsed and had things changed in the mind of the customer during that time. And then we have exchange theory. What is the respondent going to get if they fill out the survey? So we don't know if they're even going to fill it out if they don't feel that their time is being wisely utilized. And with surveys, response rate is significant. If we look at this example, response rate being calculated by returned over the sample size times 100 in the percentage, let's take, for example, the question, should ASQ continue pursuing Quality 4.0? Response being yes or no. If 100 people are in the sample and 50% respond and we get 37 yeses and 13 nos, we get a 74% positive feedback. But what if the other 50 who did not respond said no? We would have a reversal. So response rate is significant in any kind of a survey that you take. And as we look at the response rate increasing, if we have the same 74-26 and we get 50 or the 30 remaining say no, we still have a yes response. So response rate is critical, and it takes a lot of time and effort to make sure the response rate is valid for a survey. If we want quick information, we can actually take social media information for the voice of the customer. The 5-star ratings that we see when people review products or services, and the comments that they make in those responses from many different sources. So we can take the text, for example, and throw it into something like a word cloud. Interestingly enough, Microsoft Office Word product has this capability. You can go into Word in Microsoft Office, and there is an add-in that will allow you to do word clouds. Then there are what are called dendrograms, where you could actually see the association of terms through branches and get information about interactions of words from what you have taken off of social media and look at it. So you can't do this for everybody, so you're not allowed to go sneak in and look at the competitor's information, but you can look at social media information regarding your company, your organization, and do these kinds of things. So now what we've done is we've disrupted the survey paradigm and enabled text analytics to be done through taking social media information. The next thing we can look at is the value stream map. As you can see here through this animation, discrete event simulation software can be used to take your value stream map and actually watch how things progress through the process. This does a couple of things for you. One, it can show you how the process is moving, and two, it lets you automate theory of constraints. So anyone who has read The Goal by Goldratt understands the theory of constraints that Goldratt has taught for many years. So now let's look at this in another way. Here's a piece of software that actually does discrete event simulation. At each one of the nodes in the process, so you put your value stream map into the software, here's your flow, you can actually see in the value stream map the different nodes in your process. The benefit here is that if you're doing something, for example, like a Kaizen event off of your value stream map, you can go out and collect data at each of these nodes, samples of data, and estimate the distribution. Is it a normal? Is it an exponential? Is it a Poisson? What's the distribution of how things are being processed at each node? Then you can program that particular distribution in and run a simulation. And what it does is then it can show you where are your constraints. So where's Herbie? If you've read The Goal, you know that Herbie is the individual in the book, The Goal, where the author finds where and how to find the constraint. I'm going to switch over for a second and show you another piece of software very quickly. This particular piece of software actually gives you the ability to see how a process works. This happens to be an emergency department in a hospital, but you can actually see how this works. You can look at it. It gives you the ability to put in labels so you can see the nodes in your process. You can actually see node labels and see how things move through your process. So discrete event simulation gives you the ability to simulate what's going on at each step of your process, and there is software like this that allows you to actually see how things are moving. There are examples here that I have for manufacturing. This one is one of the most visual that I use when I'm looking at giving a short talk. See if we can get back to where we were. There we go. So that's discrete event simulation for automating value stream maps. The next thing to consider is the disruption of Pareto diagrams. I know Pareto diagrams have been sacred to us for many, many years, and their sacredness comes from Dr. Duran discovering how to use the Pareto diagram for quality purposes. Historically, when we taught Pareto diagrams, we were given three types of values for the y-axis. This one shows frequency, which is what we use mostly. But originally, when Duran taught this, he taught this with three possible labels or values for the y-axis: frequency, time, and cost. We've continued to use frequency the most because it's the easiest data to get. And again, with technology, we now have the ability to go into Duran's other two areas of cost and time. How much is which of the defects is the highest cost? Which of the defects takes you the most time to recover from? And you can do a Pareto on each of those. Through the years that I've been teaching this, I've not yet seen anyone use time or cost because the data is too difficult to get. If you go to my LinkedIn page, you'll see that I've done a short paper on what I'm going to show you next, which is instead of using a Pareto diagram, using what's called a network diagram. What a network diagram does, and let's look at the legend, it says the node size is the cost, the node color is the count, the width of the line between these nodes is the labor dollars, and the color of the line is the material cost. So now we have 4 different variables we can look at in this network diagram. So what are we looking at? This happens to be an automotive example. Platform means what kind of vehicle is it? Is it a car? Is it a pickup truck? What is it? We also have the engine type and the model year. So we have 3 categories, and we have these variables. So if we look at it, the claim dollars and the count, the largest is passenger cars. So the warranty cost for this particular automotive manufacturer is passenger cars. Next is pickups. And now we see that the largest claim for engines is 8 cylinders. So passenger cars with 8-cylinder engines. And it has a wide line, so it has a high labor cost. Over here, we look at a very small contributor, the turbo. The reason we look at the small one is, what is it that we're doing right in the turbo that we could take that information and extrapolate it back to the 8-cylinder engine? So we have the ability now to not only see what is the highest cost, but what is the lowest warranty cost. So we've got a lot of information here in one diagram. We see passenger cars and the relationship to pickups, the engine type, and the labor cost that we're having. So now let's take that down to the next level, drill down, and look at 4-cylinder claims are high, 8-cylinder claims are high, so both the 4 and 8-cylinder, and the 2008 model has high claims. So now the information we've got about passenger cars, 8 cylinders on one side, now we see the 8-cylinder coming up again, and it's 2008. And the 2008 4-cylinder, the connecting line there, is the widest for material and labor cost. 2009, and look at the little tiny circle for 2006. So what happened between 2006 and 2008 that's giving us high warranty costs? Did we make a model change? Did we make a supplier change? What happened over that period of time that gives us this added information? So the network diagram is very powerful. If you think of what you would have to do to get this information out of Pareto diagrams, peeling it back, as we say, peeling back the onion, how many Pareto diagrams would you have to have created to get this kind of information? And again, if you go to my LinkedIn page, I've done a mini paper on exactly what I just described for you here. So now let's look at the analytics value chain. Let's start looking at some things that go into machine learning and predictive modeling and the power that we have with that for the analyze phase of DMAIC. So it's a process within DMAIC that's very similar. Defining the problem, how are we designing the solution, which goes back to my days as a statistics major, when we were told to analyze our data before we collected it. Meaning, if you know what the objective is, what kind of analysis tool do you need? Is it a regression problem? Is it an analysis of variance? Is it a cluster? So basically, you find your objective and figure out what type of solution you're going to run. Getting the data prepared, executing it, interpreting, presenting, And most importantly, once you've got that information, what's your change management scheme if in fact changes need to be made? So let's take a problem here of looking at cooking utensils, cooking pans. Most of us cook, and probably many of us have coated pans. So this is an example of a designed experiment versus machine learning to come to the answer of why the coating is peeling off these pans. I call design of experiments isolated analytics. You can only look at a few variables and a few data points. You don't have the money to go in and look at a lot of data, versus machine learning, where if you have a data warehouse, a data repository with a lot of data in it, you can fit models and you can look at many variables and many records. So let's see what the comparison is here. So it's an anodized coating that's peeling off. So we're looking at the solution, which is the DOE versus the machine learning predictive modeling approach. The DOE data are collected locally, whereas in machine learning, we can take data from a data warehouse. So now, part one for the execution, let's look at the DOE. A DOE, we have variables that we control. So the main factor for using a design experiment is control. You can control the X variables. You have the Y variable, the response variable. And you have noise factors that are in there, which is the error term in the analysis of variance that comes out of the backside of a designed experiment. So DOEs have some limitations, the number of variables and observations, no use of a holdout step for data, and we'll talk about that in a few minutes, what that brings to the table. And it's not necessarily a predictive model. It's an inferential model looking for differences between the X variables, not really looking to build something that's predictive. Confounding and aliasing, those are statistical terms that show up when you can't take a full design experiment, you're doing a fraction of an experiment like a Taguchi method experiment. Here's some examples that are in the deck that you'll see when you look at the recording. These are different flavors. All of them have issues as isolated analytics. So now let's look at how they looked at the problem. They looked at the coding aspect of the process. The pans were dipped into an acid bath of electricity. When they came out, they had the coating, anodized coating on them. The variables that they were able to study were the acid concentration, soak time, bath temperature, and voltage. And the variable that they used as the response is what percent of the surface area peeled off. So part two, machine learning and predictive modeling. Let's look at that aspect. So for machine learning and predictive modeling, you have data at rest. You have data sitting in the data warehouse waiting to be analyzed. That's used to create a model. So you create a model from data at rest, historical data. You use that data in motion by then putting it through sample activities to see how it performs in motion. So you've got some test sets, some test equipment that you run through, and you look at it and you use the model you've created to see how it performs. Then you can deploy that model to your organization, called analytics at the edge, or edge analytics. The best example that I have that most people understand is the fuel injection in your car. The fuel injection in your car, the engineers in quality and in the organization built predictive models to see how the fuel flows and what the variables are that are associated with that. They use test engines to take that data, put it in motion, and see how it performed and fine-tune the model. Once the model is fine-tuned to take in, say, speed, RPMs of the engine, the rate of flow through the fuel pump, then they took that model that they built and they put it in a chip that's now in your car, and that predictive model collects data from how you're driving and adjusts the fuel flow to your fuel injectors. So that little card that's in your car that controls your electronic fuel injection went through this process of being created with data at rest, being tested in test engines until it was fine-tuned and worked, and then put into your car. These are the kinds of things that quality engineers need to collaborate with the mechanical engineers, etc. Because quality engineers know the processes. Quality engineers get data on performance. Quality engineers get data from customers. If we keep the activities of IT, who owns the data, engineers who work on the physical activity of the product, and the quality engineers, if we keep them isolated and separate, it's really a travesty that we don't bring all that together. So what is machine learning? It basically iterates through models, automatically does things to do things like imputation. It says, if I've got missing data, what's the best way to handle that? And then it focuses on predictive accuracy over model elegance. I know when I was going through grad school, model elegance and the fit of the R squared was the key to everything in grad school. Well, I wish I'd had the ability to look at what holdout sets were all about for my thesis, because I believe I actually did what's called overfitting, and we'll talk about that in a minute. So what are the requirements for machine learning? You have to prepare the data. You have to know what algorithms you're going to use, and those are things like regressions, decision trees, neural networks. Most of them are built into R, Python, and other software packages. They're automatically built in. So what's called the citizen data scientist, which is what quality engineers are, don't have to worry about manually programming those. Then they're automated through the software, whatever you're using, and iterates through all possible models until it homes in on the one with the best accuracy. Scalability is important. The software needs to be able to handle a lot of data and a lot of variables. And ensemble modeling is something in machine learning that says, gee, maybe I want a piece of a regression and a piece of a neural network. And if I combine those together into an ensemble, I get my best predictive model. Some terminology that you can look at later is, in statistics, we have things like dependent variables, variables transformation. Predictive modeling is called a target as opposed to a dependent variable. And in machine learning, it's called a label. So this is some terminology that you'll have when you go back and look at the recording. So the machine learning approach then is to get to the data source, grab all the variables that you think are important, grab as many as you can, because one of the difficulties with design of experiments is we only use the variables that have been brainstormed as important. And we'll see in a minute what that leads to. And you can look at the process end to end and apply these machine learning algorithms. Here's a workflow that you can have to look at later that actually shows some of the visual characteristics of how machine learning works and the workflow of getting to a predictive model. Holdout sets. What this means is you take the original data, and historically, like when I was in grad school, we took the original data, we built a model, and we lived with it. Well, holdout set says, okay, I have all this data. I'm going to take part of it and use it to build a model. It's called training a model. And I'm going to take a random sample out of that and set it aside. Why am I setting it aside? Because I know what the results are. So I build a model, and if I only do this line, what it says is, okay, I build a model, and then I take the holdout set of data and plug it back in. Because I know what the true values are here, how well did the model predict the true values that I know? And that's what you iterate through until you minimize the error of reality to prediction. And so when I said earlier, it's that machine learning is about predictive accuracy as opposed to model elegance. You can build some very elegant models on the original data, but what you really want to do is minimize the error in what you're predicting. So let's go back to the automobile and the electronic fuel injection. They want to minimize the difference between what is predicted to go into your fuel injection from all the variables on your car, minimize the difference between what's predicted and what you actually need for your car to perform well. And we know that our cars perform very well, so that the predictive model must be really good. And with all of the testing they've done, they probably used the third row here where they built the model, they validated it with this data, made some adjustments, and then retested it with a second set of real data. And this is very important. You do not get this in design of experiments. It's basically what you get is what you get. So now let's look at the results or the models that were used for machine learning. We saw the pans going into the coding area. What this shows is that material for the pan had to come from an ingot of aluminum that was rolled down to the thickness of the pan. So from the end-to-end process, we can actually go all the way up to the rolling process of the metal and look at all of the variables in the rolling process as well as the variables in the actual coding piece of the process. So now we can go back up and look at all kinds of variables up here in the rolling process. So we can look at the process end to end from the time the aluminum first gets into the process all the way through to the coating. So now the interpretation, we looked at percent of the coating peeling off. I'm using in quotes, known variables were put into the DOE. I said this a few minutes ago. A DOE works well if the known variables that go into it are actually the right variables to fix the problem. So now the percent of the pans, oh, looky, there's a defect. The number of the pans that peeled and finding the predictive variables. This is very interesting because I worked on a problem very similar to this back in the 80s, and this is what got me into this whole thing about looking at data end to end. There was a process we looked at in making rolling metal for beverage cans, soda, beer, etc. And what we found was that by looking way back up in the process, we had looked at every variable. We had looked at every variable that we could think of in the DOE, and we didn't fix the quality problem. Silly buttons. We didn't fix the problem, so we went all the way up end to end and built a large correlation matrix once a week on everything from when the aluminum first came into the process all the way down to where it was made into a can. And what we found was, and I'll show you in a minute, here's how a DOE works, your analysis variance table. DOE results. The peeling remained, but at a little lower level. So some of these variables were adjusted and it helped. But now, let's look at what came out of the machine learning. Machine learning, this was the key to the whole process. This particle size variable is what's in that white liquid you saw pouring over the, let's go back a second. Oops. That white liquid is an emulsion, and it has particles in it. That was the number 2 contributing variable, because what that did was that was the variable that conditioned the surface of the metal to receive the coating. And when that was out of control, that's when we found that the coating on the pans was peeling. So when we went back and put a control chart on the particle size and when to clean out that rolling mill and put fresh emulsion in, that's what then minimized the peeling of the coating. So it was not only the strength of the metal and the acid concentration, which these variables came out in the DOE and improved some, but this was the major contributor to the coating sticking to the pan. And we were able to look at 101 variables and over 11,000 data records. We had no resource constraints. So this is what I would have you think about then, two things. One is how many more variables you can look at if you have the data in a data warehouse. And number two, what could we now do? We could now go back and create a DOE with the most important variables. So this can be a precursor to DOE and finding what the key variables are you should put in a design experiment if you actually need to control the X variables. Which ones would they be and how would you control them? Let's move on now to decision trees, another machine learning. Many algorithms out there for creating decision trees. So you've got your variables, and as they split out in peeling and not peeling pans, what this does is overcomes the issue you have with with business intelligence tools like Tableau and ClickTech, and those kinds of products are very good at drilling down and getting information, especially for the measure phase of demand. Very good for that. But what they don't do is they don't show you interactions. So with a tool like Tableau or ClickTech, you're getting OR logic. This happened, or this happened, or this happened. And you can set up alerts, but the alerts are OR logic. And I've asked this question of every one of my clients, and they've all given me the same answer. The question is, have you ever had some kind of an issue occur, an event or a deviation in your process or anything? Have you ever had that happen and no alerts went off? And I have a 100% response rate that yes, that's happened to us. We've had something happen and no alerts went off. That's because those alerts are built on OR logic. This alert would go off, or this, or this. Whereas in a decision tree, you have AND logic, which says this happened, and this happened, and this happened, and this happened, and that combination gets me to an alert that now says it's not just an individual alert that's going to tell me what happened, but it's what is the combination? Is it a combination of temperature and pressure and speed? And is there an interaction among those three that none of them would have gone off individually, but collectively the interaction would actually give me an alert that's important? You can then take that information and add it to something like your Western Electric rules on control charts, where you have the 7 Western Electric rules that say, okay, if this happened or this happened in my control charts, then I would have an out of control situation. You can then take this interaction alert and add it to your list of things to watch for in your control charting or other kinds of areas where you're looking for deviations from your process that's causing you quality issues. So now, how they work together, the DOE and the machine learning, determining the end-to-end variables, getting the machine learning analytics, and getting those key variables. And then if you need to, redesigning your DOE using those key variables. But now the thing to remember is predictive models and machine learning are not forever. If you have some kind of shift in the distribution of the data, so you've got an input that has a distributional shift, you get a new supplier, and maybe the CP or CPK is not the same for the measurement on that supplier's quality is different, that could change your model. And the accuracy model can change over time. The model can degrade. over time because of shifts in distribution or other things. The best software is what I call white box versus black box. Black box software is where the software supplier builds the model for you, gives it to you, and says, there you go. And you have to use that model because it's the only one you've got. In many cases, you have to go back to them if you want to find out if it's degraded and you want to get it upgraded, you got to pay for that. Whereas a white box gives you the tools to build the predictive models, you're trained how to do it, use it, and you have the ability with a white box type of software to say, okay, I've seen my model degrading, I need to retrain it. And with the training part and the validation part and the holdout sets, you can do that on your own in white box software. You're given all the tools, but you get to control it. Watch out for some of your alerts, they're very important. And you can take snapshots of the predicted output and look at it versus actuals, kind of like what we used to do years ago doing residual plotting, where you can actually see if things are diverging and retrain a new model and bring it up to standard. And change management. I still like Daryl Connor's model from the 90s. I studied him in the 90s. I like his change management model where basically when a change comes along, people are immobilized or they'll deny that anything needs to be changed. They'll get upset if they have to change things. This is almost like the process of grieving. People are grieving over the old process and don't want the new one. And eventually you'll get acceptance. But you've got to go through and understand change management process if you're going to change a process using the data and analysis that you've done. What are some software packages? You can look at this at your leisure. There's a ton of them out there. This isn't all of them, but there's a bunch out there. So you've got things that are open source like R and Python and RapidMiner. You've got other things out there that you would pay money for. What I would say is look at how much data you've got, how complex it is, and evaluate the software that way. Now, the issue you're going to have is that the IT department is going to want to own choices of software. And I'll tell you because I've worked for software companies, and the IT people like the newest, shiniest toy. And companies will come in and show them a shiny toy, look at how cool this software is, but under the hood, it may not have the best analytics that you need to solve your problems. Consequently, I encourage the quality people to collaborate with the IT people in trying to choose the software. And I'm going to give you a key that will knock the socks off the IT people when you come and ask them this question. Can we see the Gartner Magic Quadrant? This is the key because the Gartner Magic Quadrant Gartner evaluates software every year and evaluates it and shows what is the best software for doing various things. And if you go to your IT department and say, if you're going to choose analytical software for me, I think we should look at the Gartner Magic Quadrant and see what's there, how it performs, what does Gartner say about it, and how does it fit our needs in our company. So this is something I want to arm you with in your conversations with IT because they really can't blow you off as fast if you act like you know what you're talking about. So as we've gone through here, I've shown you some disruptive behaviors in business and analytics. I've shown you some analytics that are disruptive for DMAIC, some new ones for measure and analyze particularly. You've seen how data at rest can be used to create a model, data in motion to test the model, and analytics at the edge to put a model in place to actually do what's called the control phase of DMAIC. So in the control phase, analytics at the edge really fits into the control phase of DMAIC. Understanding the importance of machine learning, text analytics, discrete event simulation, and the importance of working with IT or OT to acquire the best software. IT is the group, and many companies only have IT. They handle the accounting, the marketing functions, the supply, all of that. Other organizations are large enough they have what's called an OT operation, operational technology. Those are folks that handle manufacturing processes, robotics, artificial intelligence. They handle the computing on the manufacturing floor, for example. So if you have both, then you should work with both. But many companies only have an IT department, and they're expected to understand processes. And the reason I'm doing these talks and talking to people is that quality professionals know the most about the products and the processes that create them, and that information is invaluable. And if you can get the analytical tools to help you improve that, you are really, really giving a big value back to your organization. I guess maybe some questions came in over the during the session. Can we handle those? Is everybody on mute?
Sure. Thank you very much again, Jim. I need to remind that there will be time, 5 to 10 minutes, for question and answers, which you will be able to use the tool to post your questions. And you can post your questions in Q&A section of the WebEx.
Okay, I saw one pop up. Improving survey response rate. The methods that I taught when I was teaching survey design and analysis is basically follow-up. If it's a mail-out survey, following up with a postcard, telephone survey, calling and asking people to please fill out their survey. Most of it's done with follow-up by either mail or telephone. Nowadays, you've got email, and you can use that, or even if you got specifics on the individual, an IM, an instant message. But it's basically a follow-up activity.
Yes, and there is one question about will this slide presentation will be available to users? For sure, I remind you that you can find the recording of this presentation at the YouTube channel of ASQ Innovation Division.
Yep. And there's my contact information. If you want to email me directly, my email address is on the bottom of this last slide, and I'll be more than happy to communicate with you. For anybody going to the International Lean Six Sigma Conference in Las Vegas, if you're going there, I'll be speaking there and can talk to you there also. And I will also be at the World Conference doing some TED Talk on this. So those are the next two places I will be available, is at the International Conference in Vegas and at the World Conference in Seattle. I'll be at both of those. The biggest thrill of my life is coming in June. I will be lecturing in Taiwan with Dr. Noriaki Kano. And having the opportunity and the privilege to be on the same stage with Dr. Kano is just the thrill of my life. For those of you who are familiar with the Kano model, he's a great guy. I've known him for decades, and being on the same program with him is going to be fantastic.
I have actually one question to ask. For machine learning approaches that you mentioned, are they specific methods in machine learning or just the ones that you mentioned, like k-means clustering, decision trees, regression?
I just scratched the surface. There are several more. There's gradient boosting. There are several. If you were to Google it, you'd find that there are many more. I touched the ones that are closest to predictive modeling because of time constraints, and some of them get into some stuff that's really pretty complex, and I didn't want the audience falling asleep. So I tried to use the ones that seem to be most applicable to most people, but there are many, there are others.
Thank you.
I tried not to get too nerdy.
If you want, you can post your questions on the Q&A section of the WebEx. Okay, thank you very much again, Jim, for your participation and your presentation. I should remind everyone again that you can find the recording of this presentation at our YouTube channel, ASQ Innovation Division. Thank you all, and have a good night.